In this video, we're going to look at finding the area between curves by integrating with respect to y. It is sometimes easier to calculate the area between two curves by regarding x as a function of y and using horizontal rectangular elements and adding up these rectangular elements, these horizontal rectangular elements in the y direction. So the definite integral will be area is equal to integral from, and these are y values, y equals c to y equals d, right function, which is f of y, minus left function, which is g of y, dy. Or more generally, area is equal to integral from c to d, x right, minus x left, integrated with respect to y. So once we find our horizontal slice, once we define it in terms of a definite integral, we add it up in the direction of the y-axis. We add up the horizontal slices vertically, and we find the entire area. We find this whole area here. All right, so here's an example. Find the area enclosed by the parabola x equals y squared and x equals 2y squared minus 1. So the first step is finding the intersection point of x equals y squared and x equals 2y squared minus 1. To do that, we're going to let x be equal to x. So we get y squared is equal to 2y squared minus 1. Bring everything to one side, and we get negative y squared plus 1 equals 0. So we have 1 minus y squared equals 0. We can factorize this. We get 1 minus y times 1 plus y is equal to 0. If we solve this, we get y equals 1, y equals minus 1. Now let's get the x values as well. X equals y squared, so x equals 1 squared equals 1, and x equals y squared, negative 1 squared is also 1. So what we get is 1, 1 as one of the intersection points, and the other intersection point is 1 and negative 1. The next step is to sketch the region bounded by x equals y squared and x equals 2y squared minus 1. Just a bit of a review as to how we draw these parabolas. X equals y squared would be a parabola that is pointing to the right. That opens to the right, I should say. That's x equals y squared. And x equals 2y squared minus 1 is similar, except it's shifted to the left. So we shift it to the left, and it's also vertically compressed by a factor of root 2. So it's going to be like this, closer to the x-axis, and shifted to the left by 1. So this would be x equals 2y squared minus 1. And let's write x-axis here, y-axis, just to be precise, and the origin. And here we have x, y, and the origin. All right, so we're going to sketch the region bounded by x equals y squared and x equals 2y squared minus 1. And clearly we have it done here. We have the intersection points. So the key is to have a typical horizontal slice, and the differential area is going to be dA is equal to the right function, which is y squared, minus the left function, 2y squared, minus 1 dy. And then we just add up these horizontal slices in the y direction, and we get the entire area. All right, so now let's set up a definite integral to calculate this area. So area is integral from negative 1 to 1 dA, and we have integral from negative 1 to 1 y squared minus 2y squared minus 1. If we simplify this, we get integral from negative 1 to 1 minus y squared plus 1 dy. Now, because this region is symmetric with respect to the x-axis, you can see this from the previous page. You can see the region that we're describing is symmetric with respect to the x-axis, so we can use the symmetry to our advantage. So the area is going to be 2 times integral from 0 to 1, 1 minus y squared dy. So let's integrate this. We get area is equal to 2 times integral of 1 is y, integral of y squared, reversing the power rule, and we get y cubed, divided by 3, evaluated from 0 to 1. This is 2 times, apply the fundamental theorem of calculus, plug the upper limit in, we get 1 minus 1 cubed is 1, 1 minus 1 third, minus, put a lower limit, that's 0 minus 0, And we get 2 times 1 minus 1/3 is 2/3. The entire area is 4/3. Let's illustrate that on the graph. The entire area, this whole shaded area, is 4/3. All right, thanks.